US Physics Olympiad, year 2022, USAPHO, final round. This examination had two parts. Part A had 3 problems for 90 minutes, and Part B also had 3 problems for 90 minutes. Problem A1. Moment of clarity. Hold your pencil horizontally by its tip. To keep it still, you will have to exert a combination of forces on its bottom and top. These forces can be viewed as a superposition of a net upward force and a pair of opposite forces. The former ensures the force on the pencil and balanced, while the latter provides a torque called the bending moment, which ensures the torques on the pencil are balanced. Since the bending moment arises from a pair of opposite forces, it doesn't depend on the choice of origin. Question A. Consider a rod of length L and mass per length lambda. What is the bending moment you must exert to hold the rod horizontally at its end? Just as each piece of string exerts a tension on the neighboring pieces in equilibrium, each piece of solid rod also exerts a bending moment on its neighbors. For these rods under heavy loads, this bending moment can be the limiting factor that causes them to break. Suppose a rod is supported at both ends, so that it forms a bridge as shown at left above. Assume the supports are simple, so that they only provide an upward force and no bending moment. In equilibrium, a bending moment will appear throughout the rod. The magnitude of the maximum bending moment the rod can exert at any point without breaking is m0, and the length of the rod is L. The bridge is loaded uniformly, with a mass per length of lambda, including its own mass. Question B. Now suppose that one support remains at the left end, while the other is a distance d greater than L over 2, away from the left end, as shown at right above. In static equilibrium, find the bending moment m as a function of m0 at distance x0 less than d from the left end. Question D. Find the value of d that maximizes the load lambda that the bridge can take before collapsing. Solution for problem A1. Solution for question A. Consider a rod of length L and mass per length lambda. What is the bending moment you must exert to hold the rod horizontally at its end? Solution. Balance torques about the end of the rod. The weight is lambda GL applied uniformly along the rod, so the torque due to gravity is lambda GL square over 2. This can only be balanced by the bending moment, so it is lambda GL square over 2, and this is the solution for question A. Solution for question B. Find the maximum possible value of lambda before the bridge collapses. So before that, just read these conditions. Solution. Let's take a look for this picture. If we take origin as a left end, so it means that x equals 0 here. On right end we have coordinate is x equal L. Let's take point on distance x from 0. Around this point we have to calculate all forces and angular momentums from external forces. There are two external forces. One is force from this left support, which is equal to lambda GL over 2, and it's going upward. And also we have weight, which is lambda GX. These two forces created two torques. One torque is lambda GLX over 2. This is clockwise. And the other torque is negative lambda GX square over 2. And negative because it's counterclockwise. So together they will give us total torque from external forces, which is this expression. And these two torques from external forces, they must be compensated by internal bending moment. So it means that this bending moment must be opposite to this one, which is this expression. Finally, we need to find what is the maximum for this function in absolute value. That will be for x0 equal L over 2. So finally, m0 equal lambda GL square over 8. And lambda will be 8m0 over GL square. I can notice that same result we will get if we take in account all forces and torques from right side to point X. And this is obvious because the bending moment from left must be equalized in the same point by bending moment to the right. So this was a solution for question B. Question C. Now suppose that one support remains at the left end while the other is a distance d greater than L over 2 away from the left end, as shown at right above. In static equilibrium, find the bending moment m as function of x0 at the distance x0 less than d from the left end. Solution. Here, for static equilibrium, we need to equalize total force and total torques to 0. So, total force from right and left supports equal to lambda GL. Now, let's count what is the torque around any point. Let's take left support as the origin. We have torque from the right support equal Fr multiplied by d. And that's equal to weight torque from left part to torque from all weight, which is lambda GL square over 2. From here we can find that Fr equal this expression and Fl equal this expression. Now let's count what is total external torque to the left from the point x0. That will be torque from left support, which is Fl x0, because it's a clockwise. We need to subtract counterclockwise torque from weight, which is lambda g x0 square over 2. And our bending moment must be opposite to this one, which is this expression. That was solution for question C. We just need to emphasize that d must be more than L over 2, because if it's less, in that case we have to put negative force on the left side or just push it down, which is not question of this problem. That was solution for question C. Solution for question D. Find the value of d that maximizes the load lambda that the bridge can take before collapsing. Solution for this question. If the bridge doesn't collapse, then the magnitude of the bending moment must be less than m0 everywhere throughout the rod. Consider how the bending moment varies as one moves from the left end of the rod to the right. It begins at 0 when x equals 0, in the expression which we got in question C. Then reaches a positive maximum somewhere between the two supports when first derivative from this function equals 0. This occurs when x equals L minus L square over 2d, at which point there is a bending moment of m1 equal this expression. As a check, we recover the answer to part B when d equal L, and this is correct. Continuing rightward, the bending moment decreases, passes through 0 at some point x less than d, and then becomes negative. This change in sign is necessary to support the part of the rod hanging to the right of the right support. At point x equal d, the bending moment does not change discontinuously, because the supports provide no bending moment. It then smoothly returns to 0 as x approaches L. Therefore, the most negative value of the bending moment occurs when x equal d, giving the bending moment of magnitude m2 equal this expression. As another check, this matches the answer to part A for a rod of length L minus d, which is correct. As we move the right support closer to the center, the middle of the bridge becomes more stable, since m1 decreases. At the same time, m2 increases, because more of the bridge is hanging off the edge of the right support. The bridge will not collapse as long as both of these quantities, m1 and m2, are less than m0. Thus, when the right support is placed most efficiently, both of them will become equal to m0 just before the bridge collapses, which means we should have at some point m1 equal m2. Equating them yields which gives the answer. This equation gives us solution for point D, which is d equal L over square root from 2. That was solution for question D, and here we finished discussion for problem A1.